This morning's first speaker, Professor Andrei Okounkov of Columbia University. Professor Okounkov is very well known, I think, to most people in this group, very well known in the mathematics community. He received the Fields Medal in 2006. He was my colleague at UC Berkeley before moving to Princeton University and then on to Columbia University. If I had to describe Professor Okounkov in a very few words, I would say that his personal and professional life is all about making connections. He makes connections between the Moscow School, where he got his degree in the mid-1990s, and the New York School of Representation Theory and Algebraic Geometry. His Fields Medal citation cites him for making bridges between probability theory, representation theory, and algebraic geometry. This morning, again, he's talking about connections. He's talking about the crossroads between enumerative geometry and representation theory. Professor Okounkov.
So, good morning. I'm really honored and humbled to be addressing this audience, and really worried. So, but for example, let's see how this slide transition goes. Oh, it's okay. So, so Lie groups obviously are one of the very cornerstones of mathematics and mathematical physics, and since its very birth, the subject has been constantly looking to expand its range of, its scope and its range of application. As an example, one can take the theory of algebraic groups. So simple finite-dimensional Lie groups have been classified a long time ago in terms of a certain graphs called Dynkin diagrams. And their elegant structure not only shaped many developments in mathematics, but also prompted constant search for the right infinite-dimensional generalization, the right infinite-dimensional class of, the right infinite-dimensional theory of Lie groups, Lie algebras. And a lot of that was coming from mathematical physics, and concrete computation mathematical physics prompted many developments in Lie theory, such as, for example, the great success on conformal field theories that describe critical phenomena in 2 dimensions, prompted deep study of very thorough Lie algebras, affine Lie algebras. The affine Lie algebras are a particular case of Kac-Moody Lie algebras. And if we look at discrete, later in the talk we'll see discrete versions of conformal field theories. And those discrete versions described by quantum group analogs of affine Lie algebras. Today I want to talk about a very recent set of ideas that again link mathematical physics with Lie theory, but now in a new and much more expanded sense. This is originated in the study of supersymmetric quantum field theories in dimensions less than 4. We live in 4 space-time dimensions, and in physics is very different in different dimensions, and in dimensions fewer than 4, there are many more interesting theories, many more interesting gauge theories, for example. And this is going to be a talk about a subject that is still forming. And here to help you get a visual sense of the idea is a picture of how stars are forming. And you see that this is still taking shape, but we know for certain it's going to be beautiful. And see the definition of a Lie group and a Lie algebra. This is a very simple definition, and it stood the test of time as describing very important and very natural classes of objects. Our current definitions and the current boundaries of what you see in these visuals are much more smudgy, but this is work in progress, and I'm very excited to report on that. And so I'm standing here in front of you as a representative of a very large field and a representative of many people with whom I had the pleasure to collaborate. And very often when we in mathematics, we talk about ideas that originated in mathematical physics. We just say physicists. But I would like to put some concrete names to that general notion. In particular, I'd like to acknowledge the contribution of Nikita Nekrasov and Samson Shatashvili on the development of the subject. And similarly, later in the talk, there is a very important notion of duality that generalizes the classical Langlands duality in the subject. And this ideas of duality perhaps should be traced to a very old and pioneering paper of Zybrick and Interrogator. And that, of course, since has been studied by a great many people, listed here, but also not listed here, but I urge everybody to attend the talk by Misha Finkelberg in this ICM. So it may be easier to explain what's new about this new theory. It may be easier to explain which highlights of the late 20th century Lie theory are being generalized. And before, let's remind ourselves what's a Weil group, what's a Hecke algebra, and as the generalizations of these notions will be central to what I'm going to explain. So finite and discrete reflections group W of a Euclidean space appear in Lie theory as finite and affine Weil groups and play a key role in both in classification and in representation theory. Here you see the reflection hyperplanes of the simplest non-abelian reflection group and of its affine analog. Now, from this data, one can first build what's called the Bray group. This is a real arrangement of hyperplane. You take its classification. You remove the hyperplanes from the complex vector space of the same dimension. You take the quotient by the Weil group, and the fundamental group of that is the Bray group. Like an example of this is if you in this red path that you see, it joins a point and another point in the same W orbit by going in the real plane and then crossing in, say, positive imaginary. So this gives you a Bray group, and if you want to go to something called the Hecke algebra, then you make this Bray group generator satisfy a relation that generalizes the relation that reflection relation, the relation that this squares a identity. And so now back to the description of various highlights of the late 20th century Lie theory. And one of them is the McDonald-Chernyk theory. So irreducible characters, of course, in representation theory, irreducible characters are one of the most important objects. And they and also spherical functions that are also very, very important are maybe studied as eigenfunctions of invariant differential operators. And in McDonald-Chernyk theory, these invariant differential operators are replaced by certain Q-difference equations that associated. These Q-difference equations are associated to root systems and involve additional parameters for every root system. So these functions, the solutions of these Q-difference equations are remarkable multivariate hypergeometric functions, and they're terminating analogs, when this is to say analogs of characters of fine-dimensional representation. This is where the series terminates and becomes a polynomial. This is known as McDonald polynomial. And similarly to how irreducible characters are all over mathematics, these McDonald polynomials have found numerous applications in combinatorics, number theory, probability theory, algebraic geometry, etc., etc., etc. And the algebraic backbone of this theory is a certain double version of affine Hecke algebra. So it's like the Hecke algebra we saw in the slide, but it's doubled in a certain sense. And this has been constructed by Chernyk. And this has a fundamental symmetry that on the level of special functions reflects itself as a symmetry between the label and the argument of McDonald polynomial. So a very, very simple, silly example. This is a kindergarten example. Take monomials. Monomials satisfy an elementary Q-difference equations. So this is, but they also satisfies the symmetry. The symmetry is general. So if you the symmetry indicated in the slide, of course you can check it in your head, but this is the general shape of symmetry between the label and the argument of the special function. And this is very important in application, like for example in the theory of McDonald processes and so forth, that the application is probability. That is a very important feature. And this duality is a preview of the kind of duality statements that hold in general. So the next is about, I want to say a few words about Kazhdan-Lustig theory. That's in its basic form, it describes irreducible characters of irreducible highest weight modules of a Lie algebra. in terms of combinatorially associated Hecke algebra. And so I would like to use this opportunity to congratulate Kashiwara-san, who's been always a great personal inspiration for me for being awarded the Chern Medal of this ICM. So also I'd like to urge every one of you to attend the talk by Jody Williamson for the view from the heights of the modern Kazhdan Elliptic theory. And also in one of the edits of the slide, I lost the name of Ginsburg from this slide, for which I apologize. So more about this later. And another chapter in modern representation theory has to do with Young-Baxter equation and quantum groups. And so Young-Baxter equation is originated in the study of two-dimensional models of statistical mechanics. Now, roughly, quantum field theory is the study of fluctuating fields that fluctuate over a continuous space-time. Now, if you replace, maybe it's a sign I should take a drink of water. So now, if you replace the continuous space-time, you can still have. If you replace the continuous space-time by a grid, you can study now degrees of freedom that fluctuate over a grid. So in vertex model in particular, the degrees of freedom are attached to the vertices of a certain grid, and they take finitely many values, so their Hilbert space is finite dimensional. And the interaction of these degrees of freedom happens at the vertex. And the interaction between all possible values of your field for edges of this vertex are described by a certain matrix that's called, in this case, it's called R matrix. So I want to say that there'll be many connections between this talk and the talk by Rahul Bandaripande yesterday, except the R matrix means something very, very different in this subject. This is, he had an R matrix, and there'll be many R matrices here. Those are fundamental, in some very deep sense, they're related, but very different objects. So this is the definition of what a vertex model is. And Young-Baxter equation is an equation on this interaction. It's a constraint on an interaction, and Baxter noticed it's important for exact solvability of the associated vertex models. And so this is it's very important for quantum field theory to satisfy some form of covariance under transformation of spacetime, such as the conformal invariance. And Young-Baxter equation you can view as a discrete analog of such transformation invariance when your grid is being locally rearranged around a triangular grid. And so this, of course, led to many spectacular developments, again associated with Kashiwara-san. And this, the whole theory of quantum groups. But if you've never seen a quantum group, but you can imagine what an R matrix is, and we'll see an example of R matrix later, then you can reconstruct an R matrix from a very simple construction that goes back to the Leningrad School, and in particular to Rashid and his collaborators. So if you have, so maybe let's go back here. So an R matrix, so there's a vertex, and there are 4 adjacent vector spaces. That is to say, it's a matrix that acts from the tensor product of 2 vector spaces to the tensor product of 2 vector spaces. Now, if you have a matrix from the tensor product to a tensor product, what you can do, you can take a matrix element in one of the spaces and get an operator in another. So from one matrix, you get a whole supply of operators in some vector space. And this supply of operators is what generates the quantum groups. This is a very simple procedure to go from an R matrix to a quantum group. So particularly important are R matrices that additionally depend on what's called spectral parameter. Spectral parameter is when you have a variable associated to each line of your grid, and then such as U1 and U2 in this picture, and then the R matrix depends on the ratio. So by this reconstruction procedure, such R matrices give analog of quantum loop groups, and they have a very rich theory because they have, by Baxter, they have very, very large commutative subalgebras that give you quantum integrals of motion and so forth. So this diagonalization of this Baxter subalgebras of this quantum integrals of motions, this amounts to describing the spectrum in some quantum theory, and this general field of studies goes by the name of beta ansatz, and many brilliant minds have worked on this over the years. So more generally, it's a more general problem than diagonalization of these Baxter commuting operators, there's an action. If you have an R matrix that defines for you an action of, in fact, of a fine Weil group. So it's like a Weil group, except it contains a whole lattice. And this is the way you get construct a lattice operators is like this. You imagine you are on a cylinder, and you have a strand that goes around the whole cylinder, intersecting each strand once. So you have a product of R matrices. It's easier to represent this pictorially like this than to write formulas. So you have a product of R matrices, in this case 4 R matrices. And then what you get to do is you get to shift one of the spectral variables. This is called, this variable U called spectral. You get to shift one of them by an arbitrary parameter. This is the new parameter in the theory. And you additionally get to act by an arbitrary element Z that satisfies the equation below. It has to commute with the R matrix. And such operators Z typically, they come from the Cartan subtorus in your. So this gives you a difference operator. And the solutions of this difference operators, this is called the quantum conditioning homological equation. And this is, their solutions is a problem strictly more general than diagonalization, strictly more general than beta ansatz. And this is a problem that, in particular, will be geometrically solved later in the talk. And so you might be more familiar with knot theory applications of quantum groups, and the way you go there is you have this matrix depending on a spectral parameter or on the ratio of two parameters associated to two lines in your grid. And then if you take a limit when this ratio goes to either 0 or infinity, you get 2 new matrices that you can associate to an over and under crossing. And this is a sense in which these matrices depending on parameters are strictly more general than like, for example, the Young-Baxter equation is strictly more general than the Reidemeister move that it becomes in one such limit. So this will be the only formula in this talk, because this is an example. This is the Sputnik of the world of R matrices. This is what associates to. This is one of the first things out there in space. So this is an explicit R matrix that acts in a 4-dimensional space, which is a product of two representation of SL, two defining representations. And the associated theory of special functions is, so the associated geometric object, as we'll see, is just the cotangent bundle to projective line. The associated special function are very classical hypergeometric function. This object is also self-dual. The simplest object has to be self-dual, because then the dual of that otherwise would have been another simplest object. So, and so on and so forth. And the relation between this R matrix and the kind of R matrices we're working on now is the relation between the Sputnik and the International Space Station. And so this is more for downloads than for posting on a slide. So now, so I told you we're gonna talk about 3-dimensional quantum field theories, and a quantum field theory is a lot of data. And in fact, we're going to look at a very, very small piece of it today. And first, so if you have a time slice of your space-time, in this case it will be a Riemann surface, then associated to that should be some Hilbert space. And inside that Hilbert space, there'll be a very small piece of exactly supersymmetric states, that are states that are annihilated by the supersymmetry operator. So we're just going to look at that space. And so this space will still, so this will depend on the space, which is some Riemann surface B. And then further, this Riemann surface might have boundaries and might have marked points. Marked points is where, if you want particles in our theory lie. So if at a fixed time, you get a point, and what you see in pink and in red is the world line of that particle, or physicists will also call it the line operator. And then if your theory manifold has boundary, then boundary condition on the boundary means there's a different degrees of freedom, a different quantum field theory that lives on that boundary, and it's coupled to the bulk theory in some way. And so this would be also imprinted in this Hilbert space. Here the boundary is in blue, so that's at a fixed. The boundary is 2-dimensional, but the fixed time slice would be just a 1-dimensional piece of the boundary of your Riemann surface. And so in this Hilbert space, like I said, we look at just exactly supersymmetric states. But in fact, even in that exactly supersymmetric states, we don't look at it as a whole. We look at just a difference, a formal difference between, so a supersymmetry operator changes the parity. It goes from the even fermion parity to the odd fermion parity. So we just take the difference between even and odd. So it's like an index, I mean, it literally is an index of an operator. So a very familiar notion to mathematicians. And we take that index first as a virtual representation of all symmetries in the problem. And then it also forms a virtual vector bundle, so an element in K-theory, of the moduli of the surfaces B with marked points and boundaries and so forth. So this notion of having some object spread over whole moduli, this has been discussed in the talk by Rahul yesterday, and in fact it satisfies the kind of gluing that the cohomological field theory, except this is not cohomological, it's K-theoretic, but it satisfies the kind of gluing that he discussed yesterday as you go to the boundary. So this is like a K-theoretic analog of the kind of object that Rahul discussed yesterday. So this index is the great feature of an index of an operator. This is deformation invariant. And in particular, it can be studied not for a given quantum field theory, but in any of the corners of, so you have some parameter space of your theory, and you can study it in any of the possible corners of that. So in particular, you can study it for very, very large surface, or let's say very, very, very small energies. And how do you think about this, the lowest energies of a physical system? Well, first they're exact vacua, and then the next lowest states are modulated vacua, when you have a vacuum which is slowly changing as a function of your position. Like, for example, if the steady states of a gas, such as the one filling this room, are described by the density and the temperature, and states that are very close to the steady would be described by density and temperature as functions of three spatial coordinates. So this is like a map from your space to the space of vacua. So there's a certain space of vacua which we'll just put X, and the theory in the lowest energies may be described as the theory of maps from your space B here to that space of vacua. Now the amount of supersymmetry we want this theory to be very supersymmetric, and ideally we would like this X to be a hyperkähler manifold and the map be holomorphic. But the finer details of the theory will become important. This is a very rough description, and the finer details will become important if X itself or the map has a singularity, and these things are generally unavoidable. Algebraic geometers know that this is, if you study moduli spaces of maps, you better be prepared to deal with singularities. So it's very nice to think intuitively about quantum field theory as a theory of fluctuating degrees of freedom over some space-time. But anytime you want a mathematical formalization of these notions, this is going to be very, very technical. Even in this algebraic situation, it's still very technical stuff, if I may say so. But I'll describe it roughly. So what is it that how does this index is actually defined? There are certain moduli spaces of maps. On that moduli space, there's a certain analog of the virtual A-roof genus, something we're computing what should have been the index of Dirac operator. So if you think of a supersymmetry operator, you think Dirac operator. And we're computing something that should have been an index of Dirac operator. So on this moduli space, there's something like a virtual A-roof genus. This is an element in K-theory, and we take its Euler characteristic as a function of everything. So this is a virtual representation of the symmetries of X. And also, if you have a map from Riemann surface somewhere in some algebraic variety, that map has a degree. So this index is graded first, like I said, at first graded by representation of all automorphisms of X, but it also graded by connected, so maps of different degrees form different connected components of this moduli space. So this index additionally receives a grading by degree. And it's very convenient, and it's very important to think of this grading as, again, an action of some torus. Any graded vector space is the same as a representation of a torus. And that torus is this Picard torus, or the Kähler torus. It's you just take the Picard group of X and you tensor it with the multiplicative group. Now, there's a technical remark here that this is, to make it non-trivial, you have to have sufficiently, for this space to be non-trivial, you have to have sufficiently rich automorphism group of X. So if you're not familiar with this, you can safely avoid it. And so, for example, what is an example of X? So the best case is a gauge theory. And the gauge theory with the kind of supersymmetry we want is first a compact Lie group, G, and then some matter fields, which have to be with the supersymmetry we want. They have to be in the symplectic representation of this compact Lie group. And then X would be what's called the algebraic symplectic reduction. You take you impose the moment map for G to be 0, and then you take a GIT quotient by the complexification of that group G. And then the actual moduli space, the moduli space I was talking about yesterday, these are so-called quasi-maps. And this is mathematically very well understood construction, and it has many variations with critical loss, et cetera, et cetera. So this is a really good case. And a specific example of that is the example of Nakajima varieties. So the Nakajima varieties are these pictures that I had on the very first slide. So quiver is just it's just a multigraph, if you want. It's a collection of vertices and edges. And the group is a product of general linear groups over the vertices of your graph. And the representation involves some number of defining representation, but also some number, or fundamental representation, but also some number of what's called bifundamental representation, namely homomorphisms from one vertex to another vertex. So if you have an edge in your graph, such as the one that goes from Vi to Vj in this picture, then you have a homomorphism space as part of your representation theory. So this quiver data that encodes the bifundamental, physicists would say bifundamental matter in your gauge theory. And so this class of varieties is it's called Nakajima varieties, and their construction involves a graph that directly generalizes the Dynkin diagrams from one of the earlier slides. This is when I first saw it, I was really inspired. So for instance, the simplest graph that is not a finite or affine ADE graph is just a graph with one vertex and one edge, so the self loops are allowed. And so this theory for this simplest graph has at least two descriptions, and one has to do with Donaldson-Thomas theory, but now in K-theory. So this is Donaldson-Thomas theory is some counting of curves in algebraic threefolds, and you can count in various cohomology theories, but in particular here you do it in K-theory, and this contains this captures some very subtle information, some very subtle enumerative information that cohomological Donaldson-Thomas invariants do not capture. And maybe more strikingly, there was a conjecture proposed by Nekrasov and I some years ago that this is also the theory which is, there's a certain 11-dimensional supergravity theory in which instead of a fundamental object is not a particle, but instead its world volume is three-dimensional. And conjecturally, that is the theory that lies on this fundamental membrane of M theory. So the physical diversity of various insertions and boundaries conditions that can be imposed in this algebraic language, that becomes just a diversity of various evaluation maps. You have some moduli space, and ideally you would like to, if you have a map, you have a moduli space of maps, that should have an evaluation map to the target. Namely, if you have a map from you have a point little b in your surface B, and that object is maps to some x, then you should be able to evaluate your map at that point and get a point on x. So it's a map from the moduli space to the target. And this is as algebraic geometers know, this is hard to define, and many flavors of that. Because there are many flavors of that, and these many flavors directly correspond to many kinds of boundary conditions you can impose in your original theory. So, in particular, of paramount importance is what if we just do it for a flat space? So this is like, if you're familiar with Nekrasov theory, this is like Nekrasov theory except for in half the dimensions. So we study gauge theory or some theory in just flat space. Mathematically, think about it as a map from Riemann sphere that Rahul had in his very first slide. such that with certain conditions imposed at infinity, such a non-singularity condition imposed at infinity. And for this flat space, you can work equivalently with respect to automorphism, in particular with respect to the group C star that rotates that complex plane. So Q from the Q difference equations will be that element of automorphism of a flat space. And we're going to do everything equivalently. And there's a general principle by which what you can do equivalently for a flat space, you should be able to do for general manifold. And this is, in this particular instance, there's a precise technical passage from being able to do this problem to solving the general problem. And the fundamentals on this is maybe I take a drink of water and then we have. So again, this is we're in a flat space. We want to count maps from a flat space to some target X, and we count that as a representation of the automorphism of the target X, and also of the automorphism of the source. So this is a function. This is a virtual representation of the automorphism both of the target and of the source. An element of the automorphism of the source is denoted this little q. And now a fundamental feature is that this count satisfies a Q difference equation in all variables. So it satisfies a Q difference equation in these variables that capture the group action, and also in the variables that capture the degree, the scalar variables, or it lives in the Picard. And you can give a specific geometric description of the operators on this Q difference equation. So these are the Q difference equations you can prove. You can show abstractly they exist, and these are the Q difference equations we were going to study. So this is not the case for if you think of Nekrasov function. This is not the case there. This is specific to this situation. And so now we come to the main point of this lecture, is that these Q difference equations are generalization, in fact, strict generalization of the kind of all previously discussed Q difference equations. We have this McDonald-Chernykh equation, we have Knizhnik-Zamolodchikov equation. They're all special cases of this. So there are two attitudes to this. You can either love functions or dislike them. Of course, there's all possible combinations. But if you like special functions, you like Q difference equations. If you don't like special functions, then there's a different way to say it. There's a certain K-theoretic version of a cohomological field theory, and this enumerative theory, this counting theory, may be described explicitly by a certain new geometric representation theory. But if you project this to the world of, like if you go from representation theory to characters and the properties that characters satisfy, then you'll see that in particular that means that Q difference equations are the kind of equations we discussed before. And so in general, these algebras we're going to see are not Hopf algebras. But for Nakajima quiver varieties, they are Hopf algebras, and in fact there are certain new quantum loop groups. And for them we have the entire package that I described earlier. So first, Davesh, Molek, and I, we gave a very general construction of solutions to Young-Baxter equation that reproduces the old and produces lots and lots and lots of new examples using our theory, what we call stable envelope. So in particular, if you take any Nakajima quiver variety, that is to say any quiver that gives new solution of Young-Baxter equation, so the new quantum groups, and they act. So this generalizes the work of Nakajima. So this quantum groups they act on the K-theory of X, so that the K-theory of X is a weight space in the representation of this quantum group. And this is a quantum group for a certain Lie algebra, and this Lie algebra is not a Kac-Moody Lie algebra. So this is larger. This is much larger algebra than a Kac-Moody Lie algebra. And then the Q difference equation in certain equivariant variables were shown to be exactly the Knizhnik-Zamolodchikov equation for this quantum group. And then maybe enumerative geometers are more interested in equations with respect to the degree variable, the Kähler variables. And then in a paper with Smirnov, we've shown that this difference equation come from something we called affine dynamical groupoid. This is, don't be scared yet, there'll be discussion. And so what is what's the dynamical groupoid? So yeah, I should say that the last two statements in cohomology, we've shown them earlier with, so this two, in cohomology that was known some time ago. In our paper in fact in our book with Davesh. So what's a dynamical groupoid? So the picture is like we saw before, some hyperplanes, except they're not hyperplanes generating a reflection group, it's just certain more general hyperplanes. And to every wall of this arrangement, you associate a certain operator. This operator, so this is an operator that crosses this wall. So you have a wall W, then you have operator S sub W. This operator depends on all variables in the problem, but depends on from particular monomial. And from which monomial it depends, you read off from the equation of the wall. So if the equation of the wall, if you think this is an operator on a torus, where we always talk about Q-difference equation, they act on a torus. So if you go to the corresponding Lie algebra, if you take the logarithms, then so you think of the equation as being some linear equation in the logarithm of z. So there's one for you in the I guess I can point. So this is the linear equation. Yeah. So then this linear equation tells you which monomial you put. And the condition, of course, is like before, that the relation, if you go around a single vertex, it all multiplies to 1. This is like the Young-Baxter equation. This Young-Baxter equation is an example of that. And now, in our case, what is this arrangement? So the arrangement here is it takes place on the one hand in the Lie algebra, in the Cartan part of the Lie algebra we're talking about. On the other part, this Cartan subalgebra in Lie algebra is identified with the second cohomology of X. And then this set of roots, alpha, so alpha are the linear forms that give you this periodic arrangement of hyperplanes. That set of roots is, on the one hand, is the set of roots of this new Lie algebra, which is, like I said, it's not a Kac-Moody Lie algebra, it still has roots. So in the Lie theory sense, but since we think the Cartan subalgebra is identified with second cohomology, these roots are in fact a certain curve classes. They sit in second integral. They sit in second integral homology of X. And in fact, the positive roots are effective curve classes. And like I said, this is the relation, the Young-Baxter equation, and et cetera, et cetera. This can be seen as a special case of this relation like this here in this. And these objects naturally give flat Q-difference connections, and for every quantum loop group as we need in geometric applications, such groupoid has been constructed in our paper with Smirnov. And so what's the most striking feature here is that there's no Weil group. So this is the big important step, which I've dared to compare with the step of a spacewalk, is to go from arrangement of hyperplane generated in a group generated by reflections, or in general a transitive or an arrangement transitive under some symmetry. We go to a much more general arrangement. It may have some symmetry, such as translation. Any arrangement of this kind will have translational symmetry, and it is, it's reasonable to require that these operators are covariant under such symmetries. However, it's not necessary. It's not built starting from a symmetry. And in fact, if you look at these chambers, they're visibly different. Alcoves of arrangement are visibly different and have different properties. And the point of view that this is in the 21st century, you have to let go of the Weil group and be prepared to different alcoves being really different. That point of view I learned from Bezrukovnikov, which is I've put his name next to the man taking the first step in outer space. So this description of this Q-difference equation, so well, of course if you know explicitly Q-difference equation that a certain function satisfies, you know the function. And this gives you explicit enumerative data that you wanted to have in the first place. And this is, so this in particular gives you explicit handle on k-theoretic Donaldson-Thomas theory of threefolds. But conversely, if you input what we know from geometry, then you can prove very strong things about the Q-difference equations themselves. So in one paper with me and Aganaich, we've used geometric arguments to compute the monodromy of this Q-difference equation. Now, I know, so in mathematical physics, there are linear equations and the nonlinear equations. And in some sense, of course, the nonlinear equations are, of course, they're more important. But we try to understand nonlinear equation by somehow reducing to the linear equation. Now, a linear equation is just every linear equation and thing in itself. So you have a linear equation, its solutions, it's its solution. There's no further simplification. But there is a very general question you can ask about any linear equation. That is to compute its monodromy. This is a classical analytical problem, and we solved it with Mina in terms of elliptic R matrices. And the elliptic R matrices come from an elliptic homology analog of the stable envelope construction. And this computation generalizes many things. In particular, it generalizes the famous Conrad-Reinfeldt theorem that computes the monodromy of ordinary kinetic homological equation. No, not quantum, ordinary kinetic homological equation. And then further, if you think geometrically, you're going to get an integral representation of solution to this Q-difference equation. Integral in the sense of Riemann integral. And as I said, this is if you have a solution of Q-difference equation, Riemann integral solution of Q-difference equation, the Q goes to one asymptotics there. It's going to give you explicit diagonalization of some operators. And this is what solves the beta ansatz problem, therefore. So we've seen that the Nakajima varieties are obviously extremely rich and extremely important objects in applications, but even within the world of gauge theory, they don't cover everything. And then beyond gauge theory, there are other quantum field theory that we don't know description in terms of, well, they don't have a gauge theoretic description. And so it's important to maybe have some vision as to what's going to happen beyond. So Q-difference equation exists for rather abstract reasons. So this will be always there. And what their structure should be is that they're, again, given by very similar groupoid, except you don't have a Lie algebra, but you still have, so remember, the roots of your Lie algebra were also some effective curve classes in X. So you're still going to have finitely many curve classes in X that will be the roots of X in this sense, and they will give you the same kind of arrangement. Again, it'll have some features like that. And it'll be a groupoid associated to each one of this, to that arrangement, and that would give you the Kähler difference equations. And so this is for gauge theories. This is some work in progress. For theories beyond gauge theory at the moment, we don't have the right moduli spaces. This is a problem. I mean, we're not sure we have the right one, and this is a problem of current research even to define what is it supposed to be done for theories that are not gauge. And similarly, like I said this vertex functions satisfy Q-difference equation in all variables. In particular, they satisfy Q-difference equation in Kähler variables, they satisfy Q-difference equation in covariant variables. And the exact same structure should be there for Q-difference equation in covariant variables. And in fact, there is a very simple description of what the roots are. So this is given by some finite set. If you have a torus and you're looking for, if you're looking for a structure like this, what you need is a finite set of weights of that torus. And if you have a torus acting on algebraic variety, that there's a very natural finite set of weights, namely the weights, you take the fixed points, you look at the action in the normal bundle of these fixed points, gives you a finite set of weights, and this is going to be it. And in fact, there's a description what every wall operator should be, again, in terms of R matrices, like in the kinetic homological situation. And what should be the case, and what Min and I can show in some very limited generality, is that the new Langlands duality, or Seiberg interrogator duality, or symplectic duality, or it's also called sometimes 3D mirror symmetry, that it should really exchange the two it should really exchange the two sets of roots and the two groupoids. Again, for every x, you associate two sets of roots. One is a fine connection of curved classes, and another are the weights of a symplectic torus in the normal bundle to the fixed point, and they should be exchanged by this duality. This is, for example, if your x is t star of G mod b, then this will reduce to the actual this kind of operation. If you think of co-roots being curved classes and roots being weights, then this symplectic duality will exactly exchange this data. And so this is what general prediction of the Seiberg interrogator or 3D mirror symmetry or symplectic duality should do, is that this should exchange in particular these two sets. So maybe to make a more emphasis is that this is in classical Langlands duality, it exchanges roots and co-roots, but they live in the spaces of the same dimension. Here, there's no reason for these spaces to be the same dimensions. There's no reason for Picard of X to have the same rank as the rank of the maximal orthosymplectic automorphisms. So this is a duality between, you have some sets of roots in some vector space of some dimension, and another set of roots in a vector space of a different dimension. And the duality exchanges them. So you go, the Keller roots for X become the covariant roots for X check, and vice versa. So this is going to happen like that. Boom. You see, you have a completely new perspective on things. You see things you haven't seen before. And then, well, let's do it again. So this bring it back here. So I know this is, I could have shown many more slides. I've been going too fast. Oh, well. So I know it's very hard to ask questions in this audience, so I prepared some questions you might have, you could have asked. So first, where is the Kazan-Lustig theory? And so I told you this is from this, in the groupoids we have, that you can always take a limit. You can take the variables to 0 and infinity and get something topological. And then something under and overcrossing. And in a work with Roma Bezrukovnikov, we've shown that this is this algebra, this new operators you get. This is like a Hecke algebra, but in a sense that this is the right analog of Hecke algebra for you have a symplectic algebraic variety. One of the things you can quantize it, and in fact you can quantize it over a field of arbitrarily of some large positive characteristic. That's a very interesting theory there. And so this is in a slide, in one of the early slides, I did maybe say that in classical Kazan-Lustig theory, if you go to finite characteristic, then instead of Hecke algebra, you're going to get a fine Hecke algebra. And similarly here, if you quantize it in a large positive characteristic, you should get some version, some generalization of that. And in fact, the right generalization, as we show with Roma in a very large set of, in a very large list of examples that includes in particular Nakajima varieties, that is this great group limit of the groupoid. So you can, like I said, you start with something which is dependent on the variable, but then you can let the variable go to 0 infinity and get something like a braid group. But instead of taking limit, in fact, it's better not to take the limit. In fact, study the full elliptic theory, because that full elliptic theory, while it doesn't capture representation, it doesn't fully capture representation theory and characteristic P for finite P, but it does capture the roots of, so for representation theory and characteristic P for has analogs in representation theory when you have roots of unity. And that does capture, so this is some simpler theory, and it is captured by this difference equation, the elliptic theory. So this elliptic theory that, well, I didn't have time, I could have talked about it, I have 12 minutes to go, but so maybe the main object in that elliptic theory is a certain category of boundary conditions for our three-dimensional theory. And this category of boundary conditions, that should be the place where all the roads, where all the roads of various threads, various directions in categorification and representation theory, I think all these roads should converge there. It's, maybe there is a general principle I want to propose here, is that if you have some deep categorical truths and you'd like to project them onto the plane of special functions, then you naturally land not in differential equations, but you naturally land in difference equations. And in particular, the difference equation, or here Q-difference equation, they are capture much more faithfully various phenomena that you see in roots of unity or characteristic P, some subtle representation theoretical phenomena. And I think it's fundamentally, now I'm going to say something which, of course, I'm not qualified to say, but I think fundamentally that is the same fundamental reason that the Q-difference equations appear here, that they appear, Q-difference equations appear in the work of Peter Scholz and his collaborators. I think that there's something about them. And so I had one formula, and I'm not going to write it. So this is a question. And so I had one, and I'm not going to write anymore. But I'll tell you what kind of formulas we have. Is that in fact, these are extremely rich worlds to explore if you're combinatorially minded, because these theories. In the end, you deal with concrete functions, concrete geometric questions, and it's I wrote it here and just can read it. It's a treasure of geometric information, representation theoretic information, combinatorial information, and I have no doubt they have very valuable number theoretic information because and then again, I'm not qualified to talk about it, but then explicit. Also, I want to say there's this stable envelope that go into the definition of these R matrices and eventually go also in the construction of solution of the difference equation and so forth. They're sort of explicit formulas for them, and particularly in the work of Andrei Smirnov. So this in particular is a special case. This contains formulas for beta eigenfunction and then answers many other questions that classically have been of great interest in mathematical physics. So now, especially since we have so much time, we can go back to Earth. And in fact, I propose, I think we should get back to Earth, and I think it's, what is it going to say about this slide? Oh, it looks, so why don't we go right here? So, and it's, and there's a majestic city of St. Petersburg that's had been just selected to host the next ICM, the one in 2022, and I certainly would like every one of you to come there, and I look forward to welcoming you in St. Petersburg. So that's all the transparencies I had. So.
I think our speaker has very much justified my prediction that he would make connections. He's taken us out of our loop, out of our planet, and he's shown us the future. As we've seen, there's really not an opportunity to have questions from the floor, but I invite people to come up and ask questions directly to the speaker after the talk. Thank you very much once again.